Okay. This summarizes right here. This is just the summary of what we observed in section 4.3. So the sign of the derivative, if it's positive, the function's increasing. If it's negative, the function's decreasing. Now, when we take higher order derivatives, if my derivative is increasing, then that means the sign of the second derivative would be positive and negative, like this. Do you agree with what I just stated here? If the behavior of the function determines the sign of the derivative, doesn't the behavior of the first derivative determine the sign of the second derivative? So I'm extending this graph to higher, or this table to higher order derivatives. Now, we have a definition of concavity. It says the graph of a differentiable function is concave up if the derivative is increasing. Another way of saying that the derivative is increasing is that the second derivative is positive. Okay? Concave down on an open interval if the derivative is decreasing. Well, if the derivative is decreasing, the second derivative is negative. Now, if you've never heard of concavity, it has to do with the general shape of the graph. Concave up looks like a smiley face. If you take your hand and you cup the graph, your palm would be facing up. Concave down would be palm down. If you were going to take your hand and curve it over the curvature of the graph, you would have this shape. I can set up a table here where we look at the behavior of the function, first derivative, and second derivative. Okay. We're going to look at, not in light, I want it dark. We're going to look at the function, the derivative, and the second derivative. All right? If the second derivative is positive and the first derivative is positive, that means that the function will be increasing because the first derivative is positive, concave up. Increasing concave up has this shape. Does that make sense? Increasing concave up. If the second derivative is negative and the first derivative is still positive, now this shape is increasing concave down. There's increasing concave down. If the second derivative is positive and the first derivative is negative, the function is now decreasing because the derivative is negative, concave up because the second derivative is positive. Decreasing concave up has this shape. Okay, I can do better than that. This shape. Right? And then if the second derivative is negative and the first derivative is negative, the graph would be decreasing concave down. And that's this shape. Do I need to write out in words what these shapes are? Or you can, it would help, wouldn't it? Okay, fine. This is increasing. Can I do it like this? Concave up. Increasing. Concave down. This is decreasing. Concave up. And decreasing. Concave down. Is it okay if I do it like that in the table? You'll be able to read it? Okay. All right. Now, we have a second derivative test for concavity. Basically, it says let y be a function of x be twice differentiable, meaning the second derivative has to exist. And if the second derivative is positive, the graph is concave up. If the second derivative is negative, the graph is concave down. Right? That's what I just told you earlier. More the same. So if the graph is concave down, like we see right here, you see that your first derivative is going to be increasing. It's going up. If the graph is concave up, this derivative is decreasing. It's getting smaller as we roll along the curve. It's getting closer to zero. graph is concave up, the derivative is increasing. I think it's easier to understand that table that I just drew. Example 1, we want to identify the inflection points. Ooh, I didn't tell you what inflection points were. I guess now's as good a time as any. Inflection points are points where the second derivative is equal to 0. This is where the graph switches from concave up to concave down. Inflection points are where the graph changes concavity. And any local max and mins. All right, so here is the function, and we want to know where are the inflection points. Well, if we're going to have inflection points, they're going to be where the second derivative is 0. So we start with y equals 1/3 x cubed minus x squared minus 15x. Let's take the derivative. The derivative here is going to be x squared minus 2x minus 15. By the way, that factors. That's x minus 5 times x plus 3. Guess where your critical points are? Negative 3 and 5, right?
Yeah.
That's the first derivative. The second derivative is going to be 2x minus 2. Guess where you have possible points of inflection? Right? Bless you. Yeah, if x is equal to 1, 2 times 1 is 2, minus 2 is 0, right? So, it looks like we have a maximum right here at negative 3. And a minimum at 5. And it looks like we changed from concave down from negative infinity to negative 1, and concave up, not negative 1, positive 1. From 1 to infinity, because x equals 1 is a point of inflection. That's this point right there where we switch from concave down to concave up. And the only way we could have told that that was going to be at x equals 1 was by looking at where the second derivative was 0. You can't tell just by looking at this graph. Yeah, I'm not magic, contrary to popular belief. I could tell that that point of inflection was at 1 because that's where the second derivative right here was equal to 0. Okay. To get this point right here, you set the second derivative equal to 0 and solve for x. Right here, to get the critical points, we set the first derivative equal to 0 and solve for x. Any questions? Oh, well, now they give us the definition for a point of inflection. They, me, it's not really the best order. Point of inflection is where the graph of the function has a tangent line and where the concavity changes, or the graph of the function. All right. Point of inflection is where the second derivative is either equal to 0 or fails to exist. So it's kind of like a critical point, only for the second derivative. Okay? Example 2. Find and graph the coordinates of any local extreme points and inflection points on the function y equals x cubed minus 3x plus 4. Okay. What do I need to do first? So we get y prime equals 3x squared minus 3, but that is 3 times x plus 1 times x minus 1, because when you factor the 3 out, you end up with a difference of 2 squares, which factors thus. The second derivative is equal to 6x, right? Yep, it is. So where are our critical points? One and negative 1. And we have a possible point of inflection at 0. Okay, when x is equal to 0, what is y equal to? 4. So we have a point right here at 0, 4 that we expect to be a point of inflection. And when x is equal to 1, what's y? How do I find f of 1? It's 1 raised to the third minus 3 times 1 plus 4. 2. Positive 2. So that's a point at 1, 2. And f of negative 1 is negative 1 cubed minus 3 times negative 1 plus 4. So that's 7 minus 1 is 6. Right? Negative 1, 6. So we know that our function has to pass through these points. What do we know about the shape of the function between these points? Well, this is why God gave us a brain. I want to find the shape of the function within these regions. So I've got negative 1, 0, and positive 1. So this first interval is going to go from negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. I want to get the shape of the function by looking at the signs of the second derivative, the derivative, and then I can look at the shape of the function. Between negative infinity and negative 1, the second derivative is going to be negative, isn't it? Because it's just 6. Between negative 1 and 0, the second derivative is negative. Between 0 and 1, the second derivative is positive. And between 1 and infinity, the second derivative is positive. The second derivative is just a positive number times x. So whatever the sign of x is, that's the sign of the second derivative. Make sense? Now let's look at the first derivative. Going up here to the first derivative where I have it factored. If x is between negative infinity and negative 1, let's say negative 2, that gives me a negative times a negative is positive. If x is between negative 1 and 0, let's say negative 1/2, that's going to give me a positive number times a negative number. The derivative is negative. Between 0 and 1, the derivative is negative, because 1/2 minus 1 is negative, 1/2 plus 1 is positive. And between 1 and infinity, the derivative is positive. So what does that tell me about the shape of this graph? It is increasing concave down. It's decreasing concave down. It's decreasing concave up. Decreasing concave up, that's this shape. And then it's increasing concave up. That's that shape. So we connect the dots using these shapes on these regions. So this first region right here is going to be from negative infinity to negative 1. That's this region right here. The graph has this shape, increasing concave up. Right? On the next region, from negative 1 to 0, this region right here, the graph is decreasing, not up, down, decreasing concave down. The next region, from 0 to 1, that's this region right here, the graph is decreasing concave up. That's this shape. And then the next region, I ran out of colors. Oh, green, there we go. That's from 1 to infinity. The graph is increasing concave up. All right. So I've got all of my critical values marked here. I have a local max. Of 6 at x equals -1. I have a local min of 2 at x equals +1. And I have a point of inflection at 0, 4. How did I get the y values for all these points? Plug them back into the original function. We only plug things back into the derivative if we want to know the sign of the derivative. We plug them back into the second derivative to test the sign of the second derivative. Any questions? Nope. Second derivative test for local extrema. If the derivative is 0 and the second derivative is negative, less than 0 means negative. That means that our function is concave down. It's going to have a local maximum. If the derivative is 0 and the second derivative is positive, that means we're looking at this shape right here and we have a local minimum. If the first derivative is 0 and the second derivative is 0, the test fails. We may have a max, min, or a point of inflection. This is called the second derivative test for local extrema. It's a redundant test to the first derivative test. Okay? Example 3. Determine where the following function is concave up and concave down. Now I don't care about extrema, I just want to know where's the function concave up and concave down. So how do we begin to find that? What's the first thing we do? First derivative is x cubed minus 3x squared. Second derivative, all right, I need to find my possible points of inflection so I can factor out a 3x, and that would leave behind what? So we have possible points of inflection at 0 and 2. So what do we do with those points? Well, we plug them into a number line and we check the signs of the function of the second derivative at these points. So the first interval is going to go from negative infinity to 0, 0 to 2, and 2 to infinity. I'm interested only in the second derivative now. And then I'll look at the function. Let's slide it over a little. All right. I'm going to test, what number do you want to test here? Well, what just happened? Why did it? Why is it all lit up? I don't know why it's all lit up, but it is, and we'll deal with it. This is strange. All right, from 0 to infinity, the second derivative, let's pick a number like -1. That's negative, and negative times negative is positive. The function is concave up. From 0 to 2, let's try 1. 1 minus 1, that's negative. The function is concave down, try 3. That's positive. The function is concave up. So where is the function concave up? It's concave up on the intervals from negative infinity to 0, union 2 to infinity. It's concave down on the intervals from 0 to 2. Does this make sense? This is probably the most logical thing we've done all semester, right? You're not going to go that far. Okay. Example 4. Identify the inflection points and the local maxima and minima of the function. Identify the intervals where the function is concave up and concave down. We want to know it all, but only over this interval. Okay? So that means I need to find what? The first derivative is 2 plus cosine 4x times 4. So the first derivative is 2 times 1 plus 2 cosine 4x, right? So that means that I want to know where is this thing equal to 0. So I'm going to have to solve 0 equals 1 plus 2 cosine 4x, right? This is a trigonometric equation. Now this is the range, the domain for x. What's the domain for 4x? Well, the domain for 4x is going to go from negative 4 pi over 3 to 4 pi over 3. So this means that subtract 1, that's going to be negative, divide by 2. I get cosine 4x is equal to negative 1/2. Well, that's going to be where 4x is equal to, where's cosine going to be 1/2? What's the reference angle? Pi over 3. Right, pi over 3. And cosine is negative in quadrants 2 and 3. Right? So from negative 4 pi over 3, we're looking at this angle right here. And positive 4 pi over 3 is here. Okay, so cosine's negative in quadrants 2 and 3, so that's going to be negative pi, oops, let's do the negative one first. That's negative, what, pi over 3. So that would be 2 pi over 3. Also at 4x equals negative 4 pi over 3, and 4x equals positive 2 pi over 3, and 4x equals positive 4 pi over 3. I'm using the multiple angles from trigonometry to solve the trigonometric equations. When I divide by 4, I end up getting my critical values at x equals negative pi over 6, negative pi over 3, positive pi over 6, and positive pi over 3. So my derivative is equal to 0 at negative, no, not negative. I forgot my negatives, sorry guys. No, they're right there. At negative pi over 3, negative pi over 6, pi over 6, and pi over 3. We have to include those endpoints, so there we go. That's where our possible maximum and minimum values are. That's where the derivative is equal to 0. Right? Right. What else do we have to do? Second derivative. So that was the first derivative. Now let's find the second derivative. We have the derivative is 2 plus 4 cosine 4x. The second derivative is 4 times negative sine 4x times 4. So this is going to be negative 16 sine 4x. Right? Second derivative. To find the possible points of inflection, we set the second derivative equal to 0. When I set this second derivative equal to 0, all I got to do is find where sine 4x is equal to 0, because if I divide both sides by negative 16, I end up with sine 4x equals 0. Well, once again, that's going to be where 4x is equal to negative pi. 4x is equal to 0, and 4x is equal to pi. Because sine is equal to 0 at multiples of pi. So this is going to be x equals negative pi over 4, x equals 0, and x equals positive pi over 4. Good gravy. So we have our possible points of inflection. We have our second derivative. That's where the second derivative is equal to 0. Let me just summarize this. We now have to find the inflection points, local maximum intervals where the function's concave up and concave down. Okay. So since I don't have to find the intervals where the function's increasing and decreasing, I just have to check the concavity. I'm going to make a table to check my signs of the second derivative's critical points. So that's going to be negative infinity to negative pi over 4, pi over 4 to 0, 0, nope, negative pi over 4 to 0, 0 to pi over 4, and pi over 4 to infinity. It's not infinity. Our graph doesn't go to infinity. Where does it go to? Negative pi over 3 and positive pi over 3, right? Because we restricted the domain. You got to think about these things. All right, so here's the second derivative, and I just need to know the sign, and then that'll tell me the shape of the function. So right here, between negative pi over 3 and negative pi over 4, give me a number. What is it? 12 is a common denominator. 3, 4, 6. Negative 8 pi over 3, no, 24. What I'm looking at is 3 and 4 have a common denominator of 12, but that's just negative pi over 4, 4 pi over 12 to negative 3 pi over 12. There's not enough numbers in between there. So I'm going to go from negative 8 pi over 24, which is pi over 3, to negative 6 pi over 24. And in between there is negative 7 pi over 24. That's what I'm doing. So I'm going to test x equals negative 7 pi over 24. When I plug in a negative 7 pi over 24 for x, 4's are going to cancel out, and that gives me negative 7 pi over 6. What quadrant is that in? Negative 7 pi over 6 is in quadrant 2. That's positive times a negative. The second derivative here is negative. The function is concave down. Go between negative pi over 4 and 0. I have negative pi over 6, don't I? Yeah. Yeah. So that would be sine of 4 pi over 6, which is 2 pi over 3. Sine 2 pi over 3 is in quadrant 2. Sine's positive times a negative. This is concave down. Go to the next interval. Test pi over 6. Well, that would be 2 pi over 3. That's positive, negative, negative, concave down. And then we can test 7 pi over 24 times 4 is 7, 6. Sine of 7, 6. That's in quadrant 3. That's negative. This would be positive. Concave up. I have a feeling one of these is wrong. Probably this one. 7 pi over 6. Negative 7 pi over 6. So there's negative 7. 6 pi, 7 pi over 6. That would be in quadrant 2. Sine's positive in quadrant 2. Positive. That's right. Right here. Negative pi over 6. Give me a decimal for negative pi over 6 and negative pi over 4. Is negative pi over 6 in between 0 and pi over 4? Yeah, because 1/6 is smaller than 1/4, isn't it? Yeah, it is. So if I did pi over 6, that would be 2 pi over 3. But it's negative 2 pi over 3. That's in quadrant. Oh, here it is. This should be positive. I'm sorry. Because this would be in quadrant 3. 2 pi over 3. Sine of 2 pi over 3. 2 pi over 3 is in quadrant 3. And sine is negative there, and a negative times a negative is positive. There it is. I just had to find it. So, do we have enough information to answer all these questions? Identify the inflection points. We have points of inflection at negative pi over 4 and 0 and pi over 4. We can't just assume, just because we found that that's where the second derivative was 0, you can't just assume that it's going to be a point of inflection. You actually have to do this table and check and see if the concavity switches there. Because it could be a critical point, but it not be a point of inflection if the concavity doesn't change. What would it be then? I don't know. All right. We found that. Local max and min. Okay, in between, we got to look at pi over 6. Pi over 6 is what I was testing here. That's where the second derivative is positive, concave up. So that means that pi over 6 is a minimum value by the second derivative test. This is a maximum value by the second derivative test. And this is the endpoints. So we don't know what that is. Okay? But we have a minimum and a maximum at these critical points. Okay. And the intervals where this is concave up, you can see them right above here on the chart. Concave down, concave up. And that's it for today.